Hello everyone and welcome to Easy Subnetting by JMac. So this first step we have to understand is binary, because binary is the basics of all the IP addressing. Alright, so what does binary look like? Binary looks like this. So you just have ones and zeros, so it's 8 digits made up of ones and zeros. So what does binary mean? The word binary means having two parts, or relating to, composed of, or involving two things. So, and that's why we only have ones and zeros. So a light switch is a binary object. It has two settings, on and off. Alright, so think about, how does your computer send information? You have some numbers in memory and they need to be sent to the CPU. How does that happen? So think about how information moves along the keyboard in its most basic essence. And then, why do most data pathways use a multiple of 8? So we have like 64-bit operating systems, there's 128-bit data paths, and so on. So it's always a multiple of 8, or actually 2. So 64 times 2 is 128, 128 times 2 is 256, 256 times 2 is 512. But they're always evenly divided by 8. And then here's some examples of that. So, today's DIMMs use a 64-bit data path. A 64-bit processor has a word size of 64 bits. PCIe Express has 16 or 32 full duplex lanes. So you keep seeing these same numbers over and over again. And that's because that's the way binary works. A copper wire is only capable of sending a pulse of electricity. So you can either send a pulse or not send a pulse. You can send a 1 or send a 0. A fiber optic line is only capable of sending a pulse of light. It doesn't send numbers, it sends pulses of light. So I can either send a pulse of light or not send a pulse of light. A wireless radio is only capable of sending a radio wave or not sending a radio wave. So now you're kind of understanding, and that's in its basic essence. When we take it all the way down to the core, that's what happens. The copper wire just sends a pulse of electricity for a 1, and then during a time frame, it doesn't send a pulse of electricity for a 0. Fiber optic, you get the idea. So CPUs are measured in clock rate using mega and gigahertz. So let's talk about that for a second. A hertz is 1 cycle per second. A megahertz is 1 million cycles per second. And a gigahertz is 1 billion cycles per second. So you have pathways that send in multiples of 8 and cycle rates of billions per second. So I don't know if you're starting to see this. So an electric wire can send a pulse or not. A pulse is a 1. No pulse in the time frame is a 0. The time frame is a cycle of the CPU. So the CPU has all these different little cycles. So they take a second and it divides the second up into a whole bunch of tiny parts. And each part is a time frame. So if I send a pulse of electricity in that time frame, I've sent a 1. If I don't send a pulse of electricity in that time frame, it's a 0. And your computer sends these pulses across these pathways several billion times a second. When we think about it, it's pretty amazing. So assuming you have a 128-bit pathway between the memory and the CPU, you could send 16 bytes of information per cycle. And if we remember, a gigabit has 1 billion cycles per second. So 128 divided by 8 would be 16. So a byte is 8 bits. That's why we divided by that. So 16 bytes of information can be sent from the memory to the CPU per cycle. And you might have 1 billion cycles per second. It's amazing when you think about how fast all that stuff works. Alright, so a bit, again, is just a 1 or a 0. A nibble is 4 bits, so we'll talk about nibbles in the next video when we get into hexadecimal. And then a byte is 8 bits. So binary is a number system that uses a byte to translate numbers from 0 to 255. So in total, you could have 256 total numbers, because 0 adds, and then from 1 to 255. So 255 is the highest number, but in total combinations you have to add the 0 in there. So 256 total numbers. So if I have all zeros, it looks like 0. If I have all ones, it's 255. So there are a total of 256 combinations of a byte. So how do we convert binary to decimal? So we create a number line. And the number line just starts at 1, and then we double the number 7 times to the left. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. So the number line is always the same, 8, 16, 32, 64. So now you're starting to see these numbers over and over again. It's kind of starting to hit in your head. Then we put a binary number under it, and we just add the numbers of ones. So in this case, if my binary number was 11000001, I would just add 128 plus 64 plus 1, and I'd get 193. So 11000001 is 193 in decimal. So pretty easy, huh? All right, so now I'm going to have you try it. So here you have 11110001. Convert that into decimal. So, and you can pause the video. So again, just draw that out over in paper. Make sure you have plenty of space, and then put a number line on top of it. Start at 1 on the right, and then double it 7 times to the left, and then add the numbers. So it should look like this. So 11110000 with 1, 2, 4, 8, 16, 32, 64, 128. And then 128 plus 64 plus 32 plus 16 plus 1 is 241. So 11110001 is 241. Pretty easy, huh? All right, and then just to be sure, let's have you convert another one. So same thing, we have 01011010. Convert that into decimal. And again, you can pause the video and see what you come up with. All right, so let's try it here on Microsoft Paint. All right, and then 4, 8, 16, 32, 64, 128. All right, and then our number was 0, 1, 0, 1, and then 1, 0, 1, 0. So there's a 0 underneath 120. We don't add that, so we're going to take 64 plus 16 plus 8 plus 2. So it's pretty simple. No matter what your binary number is, you just put it on a number line, and 1, 2, 4, 8, and just drop it below there, and you just add the numbers above the ones. So pretty cool. And then, oh, I'm sorry, we never figured this out. This comes out to be, I believe, 90. All right. So there it is there. And all right. So now let's work it the other way. So let's say you have a decimal like 186, and you need to convert it to binary. It's the exact same thing. So let me kind of bring this. All right. So I got my number line. So we start with our number line, and we start on the left. And then we're looking for 186. So you just need to ask yourself, does 128 go into 186? And the answer is yes. So if the answer is yes, then we place a 1 there. And then we subtract that number from 128. So 186 minus 128 gives us 58. So if I go back here and if I can put 58. So does 64 go into 58? No. So then it gets a 0. Does 32 go into 58? And the answer is yes. And then that leaves us 26. So remember, if the answer is yes, we put a 1, and then whatever's left over, we put over here, and that becomes 26. Does 16 go into 26? Yes. And then what's left over? 10. Does 8 go into 10? Yes. What's left over? 2. So then we kind of know that this one's going to be 0, this one's going to be 1, and then this one's going to be 0. So that means 186 equals 1011 1010. So pretty easy, huh? So as long as you draw out your number line, you can come up with any combination between 0 and 255. So let's say we're looking for, we'll say 193. So does 28 go into 193? Yes. So the answer is, so I get a 1. And then what's left over? 65. And I can write 65 at the top, but I'm just going to put a number here, and that leaves 1. So then I know the rest of these have to be zeros. So 193, I keep hitting the little crazy little button on there, is 11000001. So now you know how to do binary both ways. All right, so now we need to work one more. So let's do 204. All right, so the number we're looking for is 204. All right, does 128 go into 204? Remember, if the answer is yes, we do a 1. And then what's left over? I believe it's 76. Does 64 go into 76? Yes. And then what's left over? I believe it's 12. Does 32 go into 12? No. So remember, no is a 0. Does 16 go into 12? No. Does 8 go into 12? Yes. Remember, yeses are 1. And then what's left over? 4. So does 4 go into 4? Yes. And then what's left over? 0. And then once you have zeros left over, then everything else left over. So 204 equals 11001100. So pretty easy, huh? All right, so now that you've converted 104 and you've converted numbers into binary, you've converted binary into decimal, now you've got a kind of a pretty good grasp of it. Remember, you need to practice it. All these things that we show you in networking, you need to practice these different things. It's kind of like your driver's license. You know, when you first get your driver's license, you're not ready for a highway trip, you know, across the country. You know, you're still driving around in town and kind of learning things. It's the same thing with this. Now that you've got that basic grasp, you need to practice it so it kind of becomes second nature. All right, and then moving on. So remember, addressing, think about how the U.S. mail works. Every house has an address, and that address is broken down into part that's unique to the house and a part that's shared by every other house on that street. So if I live at 1313 Mockingbird Lane, 1313 on that street only belongs to my house. There can be no other house that has that number. But all other houses on that street share the name Mockingbird Lane. The internet works the exact same way. Every computer has an IP address, and an IP address is made up of a part that's unique to the user and a part that's shared by the network. IP version 4 uses 4 bytes for an address, and we call each byte an octet. All right, and then, so let's take a look to find out what your address is. So in your little box beside your Windows key, type in CMD, which is just short for command prompt. And if you enter that command prompt, it'll come up like this. And now you can type in like ipconfig, so IP, which is, you know, Internet Protocol, configuration, and we're just going to hit ipconfig and hit enter. And we can see my IP address is 192.168.50.83. All these octets, so 193, this is an octet, and then 168 is an octet, and 50 is an octet, 83 is an octet. Each of these octets can only go between 0 and 255. And then you also get a subnet mask. Now the subnet mask shows us what part is shared by everybody on that network and what part is unique to the host. A subnet mask is, in binary, it's all ones followed by all zeros. You never have a 0 followed by a 1. It's always all ones followed by all zeros. So your subnet mask is typically like 255, 255, 00, or something like that, unless you subnet. Now in this case, 255 is all one, so we know 192, 168, and 50 are all part of the network inside my house. And then my computer has a unique number of 83 because it's above a 0. So any number above the subnet mask 0 is unique to that PC, and that's his unique number. And then everything above a 255 is shared by everybody in that network. And you can't have an IP address without a subnet mask. They're always paired together. If you go into your configuration utility and you try to give yourself an IP address, as soon as you hit enter, it automatically assigns a subnet mask. Think of it as like a lock and a key. A lock is no good without a key is no good without a lock. So your IP address and your subnet mask work together to show the PC and whatever's accessing it what part is shared by everybody and what part is unique to that device. All right, we'll get into more of this IP addressing, I think in part 3. But next we're going to talk about hexadecimal in part 2.